Nice. Okay, so I think we've now covered what prior fitted networks are, what PFNs are. So now I think we're probably at a point where we can move to tab PFN. So a PFN specifically designed for tabular data.
Yeah, exactly. That is what TabPFN is, and it's we, we we talked about PFNs. You need a prior to um, explain what type of different assumptions you have on the data. So we would have a prior that creates tabular data sets in order to express our assumptions on what data sets we might be facing. So the first author of the paper, Noah Holman, he came up with this pretty ingenious method to sample structural causal models. A structural causal model is basically a model that samples a graph, and then the features are nodes in that graph, and the target variable is also a node in that graph. And then you sample connections in this graph, and you don't quite know, does the target variable cause some of the features? Do the features cause the target? Do some of the features jointly cause the target? Does a feature cause a target, and that in turn causes another feature? There's this huge set of possible structural causal models that could explain the data. And if you could identify the right structural causal model for your data at hand, then you would get much better predictions. But you don't, you just get the data, you don't actually get the structural causal model. So what we actually with TabPFN do in the end is to build the Bayesian posterior over all the possible structural causal models that could be explaining the data. And so you could have one structural causal model that's completely wrong for the data. That gets a very low probability. And so the predictions from that model would be really low weighted. And then you can have a model that matches really well with the data that gets a high probability and is weighted more highly. So that's what the true Bayesian posterior would do. But of course, the TabPFN that doesn't get to store all the 130 million structured causal models that we use to generate it. It just gets the raw data, and it has learned to actually interpolate over all these possible models, and has learned to actually approximate this Bayesian posterior in a forward pass.
A big strength here with the tab PFN approach is using generated data. So it sounded like you said
Mm-hmm.
over 100 million generated data sets
Mm-hmm.
because we don't have, unlike, say, natural language data, when you're training something like a GPT kind of architecture, you have trillions of tokens that you can train your model over, but we don't have that kind of scale anywhere near that scale in terms of high quality, well structured tabular data sets. And so you've gone ahead
Mm-hmm.
and simulated over 100 million of them.
Yes, exactly. And so we can actually really control what's going in. So we have no data leakage because we actually didn't put any real data in. So there's not any possibility that we've memorized the test data sets or something. Actually, a fun fact, I should mention this. The very first time we submitted TabPFN V1, it was rejected because the reviewer said, well, this is just that the performance is far too good. You must be doing something wrong.
Mm.
And what they thought we're doing wrong is you must be tuning on your test set. Because we actually had some complicated stuff in there that was actually like doing some gradient-based updates, looking at some real data sets, and we just dropped all that. It went an epsilon worse, and we just never touch any real data during training, and that yeah made it just so
That's
much more easy to defend than
yeah,
extending
yeah,
went through
yeah.
with flying colors.